Applied Engineering Incorporated was hired to test the toilet ventilation system. The system provides for ventilation of the toilet bowl by having a ventilation port close to the bowl of the toilet. An inlet port is positioned close to the bowl by mounting the device under the hinges of the toilet lid. The port is then attached to an evacuation fan. The fan creates a negative pressure at the inlet port. The fan then pushes the fouled air into an exhaust system to be expelled from the room or building. The theory of use is that foul odors are best removed at or near the source, rather than allowing the odors to waft through the room prior to being evacuated by a ceiling fan, as is the common practice. An additional claim is that the more efficient disposal of fouled air will reduce energy costs by reducing the number of air exchanges necessary to maintain an odorless environment. A test chamber was constructed to simulate the conditions of a single-stall bathroom. The chamber was 3 feet by 4 feet by 7 feet high. A toilet was mounted to the floor of the chamber. A ventilation fan was mounted to the ceiling of the chamber. The toilet was not filled with water. A test gas was selected. Foul restroom odors are caused by sulfur compounds, primarily hydrogen sulfide. The following table shows the relative densities of gases relative to air. The table illustrates that the sulfur compounds or odor are heavier than air. Therefore, a heavier than air test gas or smoke was chosen. Test smoke pellets were burned to create colored carbon dioxide gas. The test gas was then injected into the test chamber via the toilet's normal outlet. Test 1. Test 1 simulated the standard configuration with a ceiling-mounted fan. The TVS system was not in operation for this test. The test smoke entered the test chamber through the toilet bowl. It first filled the bottom of the test chamber and eventually filled the entire chamber with smoke. The smoke injection was then suspended. After 6 additional minutes of running the fan without injecting additional smoke, the test was suspended. A small amount of residual smoke was still visible in the chamber at the time testing was stopped. The residual smoke was primarily along the floor of the test chamber and did not appear to be dispersing. Test 2. Test 2 simulated the condition where only the TVS system was connected and operational. The test smoke entered the test chamber through the toilet bowl. It first filled the bottom of the toilet bowl. No visible constituents of the test smoke overflowed the toilet bowl. Injection of smoke was then stopped. After 15 seconds of running the fan after suspension of smoke injection, no smoke was visible in the test chamber or the toilet bowl. Test 3. Test 3 simulated the condition where the ceiling fan and the TVS system were both connected and operational. The system used the same fan to simultaneously evacuate both the ceiling and the inlet port of the TVS system. The test smoke entered the test chamber through the toilet bowl. It first filled the bottom of the toilet bowl. The visible constituents of the test smoke vapor boiled in the toilet bowl with a small amount of smoke overflowing and filling the area near the floor of the toilet. Injection of smoke was then stopped. After 1 minute of running the fan after suspension of smoke injection, no smoke was visible in the test chamber or the toilet bowl. This is a visual summary of all tests running concurrently. Here's a look at the engineer's responses to the manufacturer's claims. The manufacturer's claim that the system does a better job of removing odors has strong validity. The manufacturer's claim that the device uses much less energy also has strong validity. In conclusion, based on these tests and field knowledge of this device, the data shows that the TVS device would do a much better job of removing odors than a standard ceiling exhaust fan. Data also supports that users should be able to reduce air exchanges by 1/4 to 1/2 over conventional restroom exhaust methods with no sacrifices in air quality.